So the bound can you sources we are going so we problem as the their function There are programs that so you create the data file to store the where you can from this. Oh, now we go to the here we are going to we create the test conformity. Put directly that want to say that basis this is a test value the trial expected. So we have this. Now we are going to the trial spec place where for the solution. Here we put the that so here we can put any function. That's a directly trial spec. We start This is we are going uh, triangle. We pair with eight gamma with now we go to the the quick form. And so we here we have the course, the values. This usually here which in general is not happens. So here you fill the form. This Usually this so you source. Here the indication that this is a bit, this is a volume. Or so now you have everything. Now what do is remember that way this works is have an index. Do this on the other side of so what this function does create the operator. Then when you create this, here you have to give also a lot of. So this produces once you have a metric, solve it. So this this is a good value. Case we are going to for this Here okay, so here there is a nice. Boundary location. To here notice all the functions is appropriate. So now we are going to measure the error. So we define the error as the difference between the exact solution and the approximation. And here notice that I mentioned this thing here is a function, a function. This thing here is a finite element function. So it's something I of this. But nevertheless, SAP has extended the operator track so that takes this produce okay, something that produce finite element. So you produce so you create some error file with the author. And here we want to create also L2 L2 H1. So this is done following way. You do this integral sum sobre and here the this sum here is sort of multiplication triangle, and then you sum over all the triangles. This is a bit counterintuitive. Okay, upstairs we will sign here as pulsing, but in fact this standing. So you have to remember these gradients is have a role. So if you these binary elements, so you integrate and you so this is a way very easy. Okay, so you and here you put some tolerance -10 to ask whether these are below tolerance. Here you run it. Will be tell the scanner about this. Probably this now. Around there. So now we do a conversion test. So we take a function, complicated fixing. Here we take 1 to the. Now the gradient f so we have now function, gradient, source. So we have to repeat this calculation as before, because we have to, for the exact solution, we have to create here with the B source. So here you create the, here we are going to incorporate everything function parameter. So we change the partition numbers, so number of grids. So if we increase this number, the age, so we create meshes run more. And then we create the Lagrangian, and here we put, remember here is the order, here we change. We're using just order 1, we are 1 order. The rest is the same, with the S space, the trial space, here we put. And you increase the triangulation. These approximations to the integral for better precision. So here we are using so now A and but okay, I need for every create affine operators, we solve the error, get the norm of the error, the L2 norm, and return. This is what the function return. Write it. That we return a couple with. So this is a function. Now we run this function to another function. Have a conversion that takes values for plots. Puts everything into vector. We create these 3 vectors. And fill them with values. So we for n s some number of and so we run the numbers, take the errors, put the h is size of the triangles, and put these things to a vector. We're going to and now we get these vectors from with A elements, and this we do with K equal function finite. And now we plot. Here we have so here we plot the error against the h. So these are the dots are the points we see the blue and the green. L2 errors h. First order polynomial. No. The L2 with the 2. So this is with the second order polynomial. And this one is the first order polynomial. So when we put the second order, we increase by 3 orders of magnitude. And they run at different slopes. And this is why, because we expect the error to be an h power so for the first degree we expect this for this one and these two are the h no a beta h. Now we are going to take complete. Yeah. So the k equal to 1 is the basis. Static cars. What I think they slopes. Yes, they compute the slope here. They use a link. You want to, there is a convenient library. So function not only linear. So do this. And for the h oops. So that the h has h squares or is one less. So this way you really, once you do this, you really trust you. Of course, this is a very simple code. Generally, you will have a grid which is different, a equation which is so on. It's the same. You have to get according to your problem, get a function, call it exact, use numerical function, source for function, run it out, see what you get conversion. So this you can borrow from this tutorial and okay, let's take a break. We continue at 10:40. Questions? No questions? We continue now. Continue. Here I put the we computed first. See that here in visit you have a course in Paraview also. You have this slicing. So you can slice this mesh, which is the dimension, and slice it any place you like and see what is inside. Here you can see interior, that direction, then and you can move this up and down. I move 5. Suppose you are interested in. And there are many more things. There are plenty. Here you can contour plots, some programs, can put things in spreadsheets, you have vectors, you have volume, the mesh quality, mesh. You can, we are going to do later on, you can form some things. For instance, if you have some u, for instance, you get the gradient of, try this. Gradient might. You can get the normals, but there where you can take derivative. I think it's expression. Here you Great. We apply. Now if we go here to vector, uh, don't know what issue. Here is. Well, I don't know. I know that you can plot the gradient all. I'll show you something like that. So let's continue now. Third. Third tutorial. We are going to do up to three, maybe, and then as so this is linear elasticity. So we are these are now the variables a vector. So we know how to deal instead of a scalar with a vector. And we are solving this problem with constitutive law, that we are going to take a material with two different material constructed with two different, so they have different properties. We are going to impose Dirichlet condition in component, and how to impose boundary conditions when you have more components. So the problem is this one. So this sigma u is this function, where epsilon is symmetrizer u. So epsilon half is so sigma is you are taking the divergence, so this minus half, so let's and general sigma is complicated, as when you take the trace you get the gradient, when you take the trace, you get fractions versions. In general, some combination Laplacian. This is another way of writing this. And these problems are elliptic for some choices of parameters, because if you substitute the derivatives by a vector k, right, then let's do this case. Then this case says that k squared j plus k I, and you look for solution of this, so this is 0. And there is you can look at for ui perpendicular to k, ui is perpendicular to k, this is 0. And that means that k squared has to, so this is the only solution is k squared equals 0, so it's elliptic in that for that. And the other solution is when ui is proportional to ki, so here you get k squared kj, but you have a plus sign, so this is a sum, so the only solution is k squared equal. The problem here is when this is a minus. When this is a minus, then you get for the same, when ui is proportional to ka, it's 0. This is the case where, but the other cases are, so, and those the cases for this parameter, positive parameter. So this is an elliptic system for a vector. Vector represents the motion of a body under stress. Stress the body forms. So good shows the form. Have a rod like that, and we force it is up. And for a small change, so this is a physics. And we are going to impose some boundary conditions. First, some region u is going to be 0, so the whole vector is some other region, one of the components is going to be. Then in some other regions, the sigma scalar n is, so the sigma is derivative, so this is a sort of Neumann for the vector. So there will be a boundary, which is for Neumann's, and this is the whole boundary minus this. So this is stress. And here there are some constants. The lambda, how you get the lambda, some pascals, stress, pressure. Parameter. You build the lambda for us a couple of parameters. So the numerical scheme will do that. That indicates that you are doing fraction 2 index. Because this, remember, this thing here has a 2 index, have a derivative I sigma other thing. So the weak problem is like this. Since you are having the derivative a by part metric, get something for the b, symmetrize derivative. So now we are going to build this and this condition. We upload the Reula library. And we upload some that represents a solid. So you get a model, a version of programs, and then you have the reference. Here the difference are order 1, Lagrangian, but here you have a vector value. So we have a 3 vector, float 64, here is 0. So the test space, you do this, the model, the reference, conformity H1 that is using, and we use Dirichlet tag, surface 1, and here we have this thing. What it means here is that Dirichlet map, remember our variable is a vector. So this says that you are imposing the condition, the component 1 of the vector, not in this. And here you are imposing the Dirichlet condition on the component of the vector. That's the way they implemented this in the library. So now you have to do we have to do all the gammas for the boundary. So first we put the Dirichlet conditions. We see the G1 is going to have a value for this, and 0 for the others, but the others we are not going to use. And the G2 has value 0 for everything. So here we are impose U equals 0. So here we define the trial space. Okay, so the U with boundary pose, the Dirichlet boundary. And here we are using this Dirichlet tag. So they already have the information which were on the surface where you impose this. And now we create all the constitutive blocks. This is nothing strange, you just put these numbers. These are the numbers, the experimental parameters. These are the how they enter into the model. And then you define the sigma epsilon. It's just a function. Here we don't even know what it. And now we start doing the weak form. We define the degree. It's twice the order for doing the triangulation. Measure. And from this we create A, okay? And A is like this. Where is the epsilon? Don't understand. So the forces are the epsilon here. So this is the composition. This composition, I don't know. This is the sigma composition. So maybe they already have the, like the gradient, they have the epsilon definition. I think so, but it must be because there is not the Julia or the grid up, one of them. Because here they okay, you want me right epsilon. Copy. Symmetric gradient, okay. So it's already defined. Must be either defined in Julia or in. We can put methods here. It's a grid out function. Okay. Yeah, so they have it already defined. That's why I didn't see the definition. So we do the find the operators and solve it. And write the result here. So the result is we are saving the UH, the shear with sigma. Okay? So we can see all the things. So let's try here. Let's delete everything here. Close everything. Open. Go to the Why I'm not? Oh, the results must have everything. So we can see now the vector u, a vector. So we draw it. But let me the grid here so that we see. So this is a material. We can also, to get a better, we can get the magnitude of the vector. So here you can do and have also okay you see you can plot the component of the about the components sigma say for instance some component vectors you differential vector formally violation. So the art here is to get the grid, a good grid with it. You people know how to give them. Nowadays you can take a couple of pictures and tell the program. So now we can have a multi-material problems. That means this object we are can say okay this is made out this part and this variable. So this is a tutorial to get this. How to do. You do is you get all the labels of spaces. The tags for spaces. for, for the labels. Now you are going to find some tags, for instance, the ALU tag from all the labels that so in the grid already there are labels that is so you get all this. So now you use the parameters for the function. Change this. One you ALU tag. For the ALU you get lambda for the ALU tag. Still you get. And now you have to make a sigma which has an epsilon tag. If you are in the tag ALU tag, you otherwise you use. Now you just put in the form, in the form, put this new sigma as the tax. And when you do this operation to do the summing of finite elements handling functions that this has, will sum triangles checking the tax times. After that is the same using operators and solve and put the tag here. Have them. And here you have magnitude. Yes. I don't know. By the epsilon. Probably this. I remember you could see the material for some and here there are others. So I guess I have this. here you can see that. So one material is blue, that I guess is steel, the other is aluminum, or the other way. So you can, here with this, you can check that you are doing it. Okay, let me now subject. Time-dependent problem. We're going to do a simple problem today, and maybe tomorrow I will show you because I have to prepare. We're going to do quantum mechanics, the partial equation, possible there might be potential. Yeah. But now we are just this is this. So imagine that we want to solve it the way. So let's say we do Eulers. So n plus 1 plus times I times station parameter. We are doing finite differences to the finite Gaussian. We are doing finite elements. Just put here the metrics of finite. So here we see that the un plus 1 is 1 plus identity components I del. And this amplification matrix of this pretty bad. Generally will be bigger than 1. So we know that since we have the I here, we could use root 4. Root 4 and solve with root. That will be very good. But other thing you can do is remember that this equation preserves the L2 norm. So if we take an energy, which is this is complex, so I'll put U bar U here, dV, then E dot will be from this one you will get a minus cos bar plus U times U bar times from the other you will get plus I bar plus. And when you integrate by part twice, you see that in the boundary you will get 0. So this is preserved. If you have a potential 0 become minus I times u value plus S. So, and it's very important to keep this del 2 norm equal to constant even for the in the numerical scheme. So one way of doing this is doing the integral in the following way. You do the following: you take following to m plus 1, n plus here put t over 2 I, and here you put the average plus. So you make a semi-implicit method. So when you write in terms of the matrices, this, here you get the identity from here. This one comes with a minus IA delta t equals to un plus 1. And half here. And here you get I from here plus I delta t of 2a. Okay? Well, so now if you invert this matrix, what you get is that un plus 1 will be I over 2 to the minus 1 times I plus 2. And this thing has, if you look at this metric is diagonalizable. So you can diagonalize the whole thing here. And then this for the base, for every element of the base. Where you make this diagonal, this is 1 plus I delta j divided by 1 minus I delta j. The lambdas are real. W. And this you will see that this number as a complex number has modulus. The absolute value table. Keeps the amplification 1 so that the L2 norm. So we can use this as a method. The only problem is you have to invert. If you do it with finite differences, this is a pain because you have to invert this matrix depending on boundaries. But with finite elements, there is version. So we can do this finite. And that way also we can treat not only squares or that, but a double element. Which comes fraction. Stay with it. So let me show a simple code too. Well, it's principle is easy, practice sort of. I mean, I have it running, and now it's no longer. Still running. So we are going to solve the equation. Um, Here we put in this way. This u is the un plus 1. But we call it u because it's going to be our known. So we are going to solve this problem as a function problem. Right? You want to find this. So we are going to post it as a problem because if we have this, then this u becomes the un plus 1, the evolution. Right? And we have this property that we just saw a moment ago. Okay? So what we have to look now is solve for u, given un, solve for u this problem. Okay? So you can think of this problem as a problem that you are solving for the Laplacian of u with some lower order terms. Okay? But so you can think of this problem as Laplacian u minus I 2i, right? Because this goes here, 2i over delta t, u equals to some source which is I minus I un over delta t over plus, no, minus delta un. So these things are given, a source at every step, and you solve for this equation. So this is now your elliptic equation. So you can think that way. And then do evolution in time is just solve at every time step this problem. And now and we can do this straightforward. But the inversion of this matrix, this one, right? When you do that, you will get some metric that represents minus I2 over delta t, identity plus the metric of the Laplacian. Okay? So this is going to be your A. But this A is not going to change. So you don't need to invert this every time step, but just get the inverse of this and use it all the time. So this is what complicates things, because you have to open the operator, get the matrix A, and work with the matrix. Probably look at the grid up, they have a way of doing it. I think I just I think it's good to have the details, because you know how the things work. So this is a problem, and so you can see the weak form of the problem is this one. Okay. So this is written in weak form. So we multiply by b, integrate, then integrate by part. So mathematical problem. So you upload the grid up. Here I uploaded several things. We are not going to need, but you have the for plotting, for getting out things to plot. The mesh, this is, we are not going to use it. And we have to open the arrays, the grid up arrays, grid up reference finite elements, algebra, sparse array, spaces, finite element spaces, and the cell data. So these are part of the library that we are going to. So now we just do a Cartesian 100 by 180 times 1. And we just make, this is a Cartesian as square. And we put here, we have several possible cell data. We have a test, a bump, something down, and then we have a particle, something which is sort of something like that, high frequency, and for U, complex real set, same with some, so this is way more, so we can have something like a particle in quantum mechanics. And we save the files in. So if we have a different, this is all for organizing. Runs. So if we use test, time, save the file, bump with time, finite the number of steps, save the thing, number of particle use these things. And this n in here is how many times you save the data. Because you are here, for instance, the one I'm running here has 16,000 time steps. So I don't want to save 16,000. I will save less, 100. So you define it the dt t times first one, and here there is some information I print, which is t over dx squared. For this case, I'm running now. Because this gives some sense of it. Why? Because here we have dt over dx squared. Let me close the door because can you close? So here we have a dt over dx squared. This will be, for a heat equation, will be the CFL, because for the heat equation, the eigenvalues go like dx squared, 1 over dx squared. Have the dt, and this has to be less than 1. Less than. Here we don't have this constraint because this always converges. But I mean, this always stable, but just look at the over dx is something so that the spec that the solution quite small. But if you look at the error will, because, and this is still very, because why the error? Because if we are at some mode, we know that the solution will be this exponent here, and we are approximating this exponent by this. So if you open up this is going to be like that. So from this is the upper part, and this one will be with a plus sign here and a minus here, and while the Taylor expansion of this will be this exponent, and you see that they cancel here. These ones cancel with this to this order, and so the error is order lambda times. So how bad are we doing is so here we put Dirichlet boundary conditions everywhere. So we get the phase labeling, so all the phases of the heat, we put 0 to 1. This includes the sides and the points. That's why we have 8 and 4 here. And so then we get the triangulation, order 2 here. And here we look at the boundaries. This is just to make sure that the boundaries are okay, etc. So I put some function here to plot, but it's a trivial function. We get a reference Lagrange and everything we already know. The test and the trial space with 0 Dirichlet condition. This is the definition of the norm now. Here we have to put the contours. Here they have the particle. So you see the particle has And here you see it also. So if we are in the test, now we are going to put particle. And so this particle is a function. So now to get the UN, we have to do an interpolation of grid. So we interpolate everywhere the UN in this space. So this is the thing we do when we say, okay, we have a U in omega. Now we have a big UH. With aspect. This one, say this. So now we have a function. And we write it into dot the that we note. Have always problem here. I don't know why problem here, but this is a problem of that with something G. So here is the part that is more complicated than before. And because we want to generate a matrix. One, we're going to invert just one. So we have to know how to so we use this in this is assembler, something that create matrix out of the finite. So these are the basis of the finite element, and this is the trial base. So here this is the base where boundary, and actually in this case we are taking elements that are 0 in the and now we do the A is going to be this. So this is what we want to so we define this no wait it is so you collect all this cell matrix to bit and so you want to invert this collecting things and then you assemble it to a matrix. So here what you are doing is taking the basis here. This is going to be a metric, sort of a metric, because you are putting basis, and then you assemble this as a real range element library, but as a and so you get this method. We are going to use it to invert this. Actually, not invert this metric, but use in every case find the solution. We never invert this. For everything is say hey, we are going to have an equal. So use this to from this is fixed. We are going to have to do. So this is nothing. It's just to make equal to data. So that and then here we do the iteration in time. So you say for these steps, between one and number of steps, you take a new time, create the vector b source, okay? Here you put the un, so the solution at this time t, un here also. So this you make a vector contribution. So you put this and apply the basis. This give you a vector in the basis. Collect the data from the vector contribution and assemble. So this is a real vector, real vectoring. And now you solve, you do the inversion. Okay, so you get from the matrix A that we already compute, solve for, and given the vector B, you solve for x. And now this x is a vector, some finite elements, a vector component with elements. So now you transform this vector x to a function with respect to this finite. And so now you actualize. You say, okay, un, the new un is h, get from, and repeat. The rest is, this in here is just saving the data. And this is running from last night. I put a lot of, but I think I have is some part of it. There is something. So we can use pseudo colors, and now you see you have the real part of UH and the imaginary. So this real part. So this is the real part, the data. So it's actually the initial data. This is the first step. Away. So it's up. High frequency. Already see that bounces. So it's going this way, bounce surface. Red source. Here, for instance, you can create the function that I can rho. Rho is a function that just takes 2r squared plus the absolute value of studies. ID. So that we find in the particle and these particles. But in general, this is not very precise. Have to do another run much better error. I'll finish this thing, but I will put the notebook. Then we have another for the heat equation that we have. Questions? Are there questions? Well, so I'm going to stop now and we are going to be on questions, labs, the homework. Tell us, answer.